Today I would like to tell you how we try to address a problem that we have, and I think it's a common problem. And the problem is, well, we have a certain amount of resources, there are not so many, and we don't want to waste them, so we would like to exploit them efficiently. How to do that? Well, we have learned that we can use a cloud, and we can apply horizontal auto-scaling to our application. So we have investigated two strategies. One is to use the OneFlow tool of OpenNebula, for one big application, which is a Grid Tier-2, and the other one, which was the first that we tried to explore, is to use a custom toolkit for virtual batch farms on demand. The problem is that not all applications are scalable. I mean, for example, we have a huge WLCG Tier-2 site hosted on the cloud, and this doesn't like to scale, or at least it doesn't like to scale down. So I will tell you how we plan to solve this problem. So this is how our cloud looks like in my mind. So we have a physical infrastructure on top of which we have built some tools to allow for running of multi-tenant applications. So the physical infrastructure, at the very base we have two networks. One is the public network, and the other one is a private network on which we collapse both three things: the communication among the private networking among virtual machines, but also management and data access, all on the same network. So we have 10 gigabit per second connections on the public network and 1 giga to the servers, and 10 giga to the storage on the private network. The software we use, of course, OpenNebula. We are still using a bit old version, 4.8. Then we aggregate and export the storage with cluster. MySQL as a backend for OpenNebula and other things. Operating system for hypervisors and most of the virtual machines is CentOS 6. We use Cloud Init for contextualizations. We have actually quite basic images for virtual machines and quite complex contextualization strategy. And then we use Elasticsearch for accounting, basically, and Zabbix for monitoring. So our cloud is, let's say, medium, small. We have 73 hypervisors. It's not very fancy hardware. They are divided into clusters. So our pets are these 4 hypervisors for service hypervisors. Server class hardware. They have both a private and a public connection, and data store is for running images of running VMs. Is shared to live-for-live migration, and there's no special input-output requirements, and the file system is mirrored. While the workers are really these consumable virtual machines that we just need to compute, and then they can disappear when we don't care about. They only have a private IP, and of course they need to have a good read-write performance, and the data store for the images in this case is cached, because it cost us too much to share also this data store, and the file system is optimized for performance. We have in total 1,300 cores, which means more or less 200 virtual machines running, and the virtualization is KVM. So concerning storage, we have 1.8 petabyte of gross storage. Most of it is data for experiments, and as you can see from the pie plot, the main experiment hosting data at our computing center is Alice. And then we have a little bit of storage that is used really to run the OpenNebula infrastructure. But you see this very small, this green slice is a very small fraction of the overall storage, and we have 2 terabyte for the image data store. The image data store, as I said, is shared among the clusters, all the hosts of the cluster. And then we have a system data store for the services. This is mirrored on 2 servers and then shared among the hosts, while in the case of the worker cluster, it's cached, so it means that we synchronize by hand the new images on the local disks of all the hypervisors, and this is basically to speed up the boot process of the virtual machine. Okay, so then we have another type of storage, that this is what we call the cloud storage. Namely, we use it, the typical use case is to give a persistent home space to the tenants, and that they can export, for example, via NFS, what they generally do is to export via NFS within their own private network. And this we serve with iSCSI. We have two objects. One is a Linux server, and we use the official add-on for OpenNebula, the driver. And then we have another very old tool that in order to use it, we have to patch just a little bit the official driver, and in total we have more or less 10 terabyte of storage. So we have a multi-tenant cloud, which means we have several isolated applications running of it. The biggest one is the WLCG Tier-2, that unfortunately is also the only one in which we would like to bring as Elasticity, but we don't have yet. And then you can see the open bubbles are those applications in which we have somehow implemented Elasticity already, and you see that we have some local applications. These are really small batch farms for a theory group at our institute, Medical Images and Compass, and the idea is to bring Elasticity also to those applications. And then we have some simple virtual machine, really one single machine for example, nuclear plant simulations or ultra-fast silicon detectors or electronics. And these are really very specific, really tailored to the needs of that particular applications. And this, we don't need this. Elasticity is just one single machine. So let me start with BES3 Tier-2, which is medium, big, which is 200 cores. We try to use here the OneFlow tool, and of course we use it in a wrong way because as far as I understand, OneFlow, it works fine if you have you need to do some sort of load balancing and you don't really care about which VM you just switch off. But in our case, we have to handle a batch farm, and this is a completely different situation because the application is stateful. I want to switch off those nodes that are not running jobs. And also, we have to, or yeah, we chose to somehow, forced, to use PBS as batch system, and PBS is not cloud aware, which means that if you switch off a node, physically switch off a virtual machine, PBS complains a little bit and you can have some kind of trouble. So we say it's not cloud aware. But we chose to use this solution anyway because we have the jobs that are running on this application, on this farm have some feature, and the feature are that these are received in bunches, in trains of jobs, and within the bunch, all the jobs have more or less the same running time, which could be sometimes it's just few hours if it's a bunch of test jobs, sometimes it's a day, but still we have bunches of jobs and then resources are idle most of the time. So how to do, what to do? We use OneFlow with one service where the master is a cream compute element and the slaves are the DIRAC Grid worker nodes. Then both the rows publish to one gate and some information. The compute element published the number of queued and running jobs, while the worker nodes the queued jobs, but also their state, which I mean not the state in PBS. So if the node is online in PBS or not, because the compute elements periodically checks for queued jobs, and if there are no queued jobs, basically puts offline all the nodes. So the elasticity criteria are scale up of one node at a time if there are waiting jobs, and scale down if all the nodes are offline. So as you can see in the example, this is just a little test they have done to see if everything is working properly. You see the CPU load, the different colors are different, is the CPU load for different virtual machines. So at the beginning we start running some jobs and immediately you see the CPU load of the existing node increase, and then after a certain period you have the scale up of a second node, and then you have the cool down period, and again, and then you see that even when some jobs finish, the scale down happens only when all the jobs of all machines, the scale down of all machines happens when all the jobs have finished. But still, it's not really 100% efficient, but it's better than keeping all the resources idle all the time. And then we would like to do something similar with the WLCG Tier-2, which is 900 cores roughly. So the problem is that this application is never idle, because if you see the profile of the running jobs as compared to the, this is CPU hours on the bottom, but doesn't matter, means that there are always running jobs. More machines you put and more jobs you will have running. This is never idle. And we have to provide a minimum amount of jobs running, which is 900 more or less, constantly, but we would like to go above this pledged number if the cloud is free, but of course not to steal resources to other applications, which would give then, take then the higher priority on running. So, And also another problem is that in this case, job duration is really unpredictable. It could be a few minutes or hours, days, we don't know. So we have chosen to have a magic number of 6 cores per virtual machine, which is a compromise, not to have 2 small virtual machines, otherwise it would be inefficient, but also not too big because we need to fit them properly in our hypervisors. So the idea that we don't have implemented yet, but the idea is to have a smaller bunch of virtual machines. A smaller really means like just 2 or 3 cores, which expands and shrinks periodically. So you basically have all the time a certain amount of virtual machines which are kept in draining, so they don't accept jobs anymore and just wait for the jobs to finish. That's why we want them to have them smaller. You have less jobs running. And the big problem here is that we would like to use Condor batch system, which is cloud aware, but of course there is some work to do to implement a cream compute element with Condor. But for this we would like to use again OneFlow. While for smaller applications, so these virtual batch farms for other tenants, we have developed a different system, and this system is based on some tools. First of all, let's really start from isolating the environment for the batch farms. So network isolation is done. Each user has basically two networks. One is private, it's a full virtual network, and the other one is public, but it contains only one single public IP. And they are isolated with heap tables on the hypervisor. Then, one layer above, we have virtual routers. These have a private and a public IP on those networks. And this is just a very lightweight virtual machine that acts as DHCP, DNS, NAS, and then, well, it is under our control. The user cannot touch the virtual router, but what the user can do, the user is assigned an elastic IP, and whenever the user associates the elastic IP, so associate this public IP to one of his virtual machines, there is a custom script that writes port forwarding rules on the virtual router, so that normally we do it only for port 22, but we can customize this. Then, Elastic is a Python daemon developed by one of our colleagues. It uses this E2 interface, namely Boto, to communicate with OpenNebula. So it can work basically on any other cloud that exposes this interface. And it has a plugin implemented for Condor as well. So what the user does is to deploy one single virtual machine where in the context of this virtual machine, it writes a configuration for the master, for the different slaves, and for the Elastic service itself. And then the Elastic scales up when there are jobs in queue and scales down a specific VM when this VM is idle. And this is an example of the things you can configure, for example, Elastic parameters like the idle time and so on and so forth, and EC2, like the flavor that you use for the image, the API endpoint and credentials and some other stuff, and minimal number of machines that should always be running, of workers that should always be running, and maximum quota. So, and then we have two different web tools to allow the user to configure the Elastic batch farm in an easy way. One is provided by CERN, and it's called CERN VM Online. And you can, if you don't know much about the CERN VM ecosystem, I put 2 links here. It's basically a tool to contextualize either a single machine or a cluster of machines, and it works unfortunately only for micro CERN VM images. Micro CERN VM, shortly, is a very basic and tiny image that contains only the kernel, and then at boot time the operating system is fetched from the web. Also, there are more information on this. But of course, there are some applications that need different operating systems and some groups that really want to decouple from the CERN environment. So we have developed a small user interface, very similar to the CERN VM Online, that allows users to use also Ubuntu and CentOS images. So this is how the CERN VM Online configuration tool looks like, and this is our web interface. It's very similar. So what it does, that the user can enter, specify flavor and things. It can also specify a small user data script. It could be any kind of Mesh or Python script, and then the web application puts together all the information in a contextualization file for cloud in it, and then directly launches the master node with all the context to the cloud, to our cloud. So with these tools, to summarize, we have a model for elastic virtual farm provisioning, which is a confined application in a sandbox, deploy either with the EUCA tools or with the graphic interface, use Elastic for elasticity, iSCSI for persistent disk storage, and use the flavors, Amazon-like flavors. So we have many more flavors actually to simplify the contextualization of or the configuration of the machine. And in this, we have some little patch to OpenNebula because we use the template as files. So the flavor templates are the files. And in the file, the network is chosen according to the username. So as I said before, we also have one Elastic IP per different per network. And that's it. So this is an example how it looks like. On the bottom, you see, for example, the grid node. The application is static, and you see some holes because we had a problem with the chiller at some point. And then on the top, you see, for example, the virtual analysis facility workers. And you see at the beginning, we didn't have Elasticity implemented, so Elasticity was implemented by hand. And then when we started to implement Elasticity, automatic Elasticity with Elastic, you see the situation changes. So to conclude, well, we switched to the infrastructure as a service cloud paradigm in 2011, and this was mainly to share resources among grid and the interactive analysis facility, and this was basically to ease the management of the cloud. But then we gained flexibility and we started to have fun with it, and we started to bring several smaller applications into the cloud, our small cloud. And now we came to the point where, well, resources are not infinite, and we need to force elasticity somehow, especially because it's not easy to convince tenants to release their resources, even if they are not used. So we have investigated these two strategies, and we plan to keep OneFlow for bigger use cases, those that are under our control, like the Grid Tier-2, while using the Elastic toolkit for the user virtual farms. And what we would like to have, ideally, is a dynamical situation, saturation, yes, but dynamical, in which the applications, how to scale and continuously fill in a dynamic way all the resources available. But of course, here there is also another problem, that it's assigning priorities to some of those to those applications according to the amount of money they put into the cloud. So what happens is that we would like to have a fair share algorithm to schedule the virtual machines, which is based on a priori priorities that we assign and on the historical usage per tenant of the resources. And this is part of a project. We will start working on this in view of this grant from the European Communion that the INFN and other partners won, and I think Stefano will say more about this. Done.
Yeah.
Did you consider introducing some kind of economy to regulate the usage of the resources by the people? So obviously you cannot make them pay.
No.
But
yes.
maybe do something that looks like they're paying.
Yeah, some sort of billing. Yes, we started to work on billing, like maybe just send an email when they have exceeded, or just say, look, this month you use that, and if you switch off your resources, maybe next month you can have the double of resources. This is to give them. We try to do that. I have a little thing in progress using Elasticsearch for querying the database and doing plots and stuff, but it's not in production yet.
Do you have the virtual router available for, or do you, the virtual router did you provide with the networks? Is it available?
It's a.
I mean, yeah.
It's a virtual machine we have.
But the way it's configured, it's integrated with OpenNebula with the context or somehow,
yes.
which can be of interest for.
Yes, of course. I mean, but there is no particular reason why to use that virtual router.
Yeah,
We could use anything else. It's just our colleague did it like that in the past.
Okay.
Okay. Well, thank you, Sara.